Good morning. My name is Akshay, and I'm going to be talking about our paper, Fast and Precise Application Code Analysis using a partial library. So analysis time is still an issue in static analysis for cases like really large programs or a large collection of programs like an app store. And an application code analysis can offer a speed up. So what do we mean by an application code analysis? So here's a split up of program code. So we have the application code and the library, which consists of the standard library and third-party libraries. And for example, in the NJR dataset, we see that less than 1% of the Java code is actually application code. So there is a potential for a lot of speed up here because most developers only care about errors that manifest in the application code. Errors that manifest in the library anyways are not under the control of the developer. So a naive idea may be to simply ignore the library and analyze just the application code, but there are many errors which either originate or in the library or propagate through the library, but end up manifesting in the application code. So ignoring the library entirely is going to cause us to miss too many errors. So we need to still somehow model the library. And to quantify an application code analysis, we usually use three metrics. The first is speed up. So as compared to whole program analysis, how much faster is the application code analysis? The second is precision. So here we consider the whole program analysis results as the ground truth. So out of all the errors given by the application code analysis, how many were true positives? So this is basically the true positive rate compared to the whole program analysis. And the third metric is recall, which is out of the whole program analysis true positives, how many did the application code analysis catch? So the current best tool for an application code analysis for Java is Avros. And it functions in the following way. So the entire library is summarized in, this is an oversimplification of how it works, but Avros summarizes the whole library using a single library summary class, and it has a single summary pointer which aggregates or merges information from all the pointers in the library. And similarly, it has a summary method to perform all the callbacks that happen in the library. So since this library method is fairly small, the speed up that Avros gets is very large. And since the library summary over approximates a library, the recall is at 100%. However, precision is fairly poor at 59% because the summary merges information from the entire library and we can have many false positives. So precision is fairly low. But let's look at what user expectations on precision are. So Christakis and Bird conducted a developer study on user experiences with static analysis tools. And they concluded that these tools should aim for 80% user perceived precision. So that means the user should perceive less than 20% of the errors as false positives. But the whole program analysis themselves struggle to achieve 80% user perceived precision. So an application code analysis needs to strive for 100% precision relative to the whole program analysis. Because if it doesn't, then it's definitely not going to meet the user expectation in precision. But the best tool we currently have is Avros, which gets only 59% precision relative to the whole program analysis. So the reason Avros is designed this way is it was designed as a verification tool. So it aims for 100% recall theoretically. And given that, it tries to get as much precision as possible. But the user study shows that precision is considered more important than recall, and users have a high expectation on the precision that these tools will give. So what can we do about this? We introduced a new tool called QueryMax, and QueryMax is going to act as a preprocessor to an existing static analysis tool. So QueryMax takes in the application code, the library, and the analysis queries, and outputs a partial library. So the partial library is a subset of the library that covers most of the client analysis queries. And then we feed this partial library instead of the actual library to the existing static analysis tool, and it gives out a set of errors. So the result is that we get 100% precision because we are performing an under approximation, and we trade off a little bit of recall for speed up. So we get a 10x speed up and 87% recall. So to get a better idea of how QueryMax and the other baselines work, let's take a look at a simple example. So this is a schematic of the whole program, and the circle here represents application code. So we're trying to do a cast check analysis, that is, check if any downcast errors will cause exceptions. And the application code has 10 cast instructions. So casts numbered 7, 8, 9, and 10 get their values from within the application code, and they're not affected by any library pointers. But casts 1, 2, 3, 4, 5, and 6 are affected by are directly affected by library methods A, B, and C, which are marked in gray. The other methods, which are in white, like D and E, are library methods that indirectly affect casts inside the program. So let's take a look at the first baseline, which we've already seen, Avros. And we know that the way Avros works is it constructs a library summary which over approximates the library. So in this figure, cross represents that that method is not analyzed by Avros, whereas a tick represents that the method does get analyzed by the client when using Avros. So in this case, none of the library methods get analyzed, and only the library summary gets analyzed. But since the library summary is an over approximation, we cover all 10 cast instructions. However, the limitation is that the library summary is going to merge information from the library. So thereby, we're going to drop some precision, as we saw before. A second baseline is a demand-driven analysis. So what a demand-driven analysis does is it works on a per query basis, and it takes the backward slice from that query and analyzes just enough to answer one specific query. So what we could do here is we could run a demand-driven analysis for each of these 10 cast instructions separately. So in this case, all 10 cast instructions get answered, but we need to analyze all 15 methods in this program to do that. And the limitation here is that programs can have a few very expensive queries which have a huge backward slice. So in this case, cast 1 and cast 2 have get their value from method A, but in the backward slice, there are 10 further methods, and each of these 10 methods could further have a larger backward slice. So answering cast 1 and cast 2 ends up being very expensive. The third baseline is an application-only analysis. So this analysis analyzes only the application code and ignores everything outside. So none of the library methods are analyzed. And as a result, it only covers casts 7, 8, 9, and 10, which get their value entirely from the application code. And the limitation of this is that too many casts are not covered, and we may miss out on a lot of errors. So finally, we get to the partial library selected by QueryMax. And the idea is that we're going to select something in between an application-only analysis and a demand-driven analysis. So our partial library, in this case, is going to cover only 5 methods, A, B, C, D, and E. And this is going to be sufficient to fully answer queries about casts 3, 4, 5, 6, 7, 8, 9, and 10. Whereas we leave out the library that's necessary to answer the expensive casts, cast 1 and cast 2. So the core insight here is we cover all but the most expensive casts, and that gives us a larger speed up than a demand-driven analysis. But the limitation is that we may miss errors from the most expensive casts. Right, so as far as the applicability of QueryMax to client analyses goes, here this table gives 4 examples of clients and their possible client analysis queries. So as we saw in a cast check analysis, a client query could be all the downcast instructions in the application code. Or a second example is for a null pointer analysis, all the method calls and field access are in the application code are considered as the client queries. And the cast check and the null pointer analysis are the 2 that we'll see in the experiments that we do for this paper. So the limitations for QueryMax are that it cannot be applied to clients that want to catch errors that manifest in the library as well as the application. So, and the second limitation is that it cannot be applied to clients that cannot afford to lose recall, because we are going to trade off some amount of recall for our speed up. Okay, so getting to the data set that we use. So we use 293 Java programs from the NJR1 data set. And the advantages are that all the programs are amenable to static analysis, and the data set lists the set of application and third-party classes for every program. Out of these, we filter out programs that crash or timeout for a baseline, leaving us with 221 programs. And from this, for the fast check analysis benchmarks, we pick programs with at least one whole program cast error. So the reason for this is it goes back to the definition of recall. So the recall is out of the whole program analysis errors, how many were caught by the application code analysis. But if there are no whole program analysis errors, we have 0 in the denominator. So recall is undefined in this case. So because of this reason, we pick the 58 programs that have at least one cast error. And similarly, for the null point analysis, we pick the 177 programs that have at least one null error in the whole program analysis. So coming to the experiments for the cast check analysis, on the x-axis, we have recall, and on the y-axis, we have speed up. Speed up is plotted on a logarithmic scale. So we have a variety of baselines and QueryMax, which are plotted in this 2D space of recall and speed up. So let's start first with this whole program analysis that's in the red circle. So it gets no speed up trivially compared to itself, and it gets 100% recall again trivially, since it is the ground truth which we compute speed up and recall against. The second point is the application only analysis. So it gets 254x speed up, which is really large because it analyzes the application analyzes the application and ignores everything outside. And since the application is quite small compared to the library, the speed up is large. But we obviously miss out on some errors, and we get a recall of 56%. The next point is Avros. So we know how it works. It gets a speed up of 179x, and it's the only tool that gets a precision of 71%. The other tools get 100% precision because Avros is the only tool that does an over approximation. And the recall is 60% instead of 100% because of a particular bug in the Avros implementation. The next point is a demand-driven analysis. So it gets a pretty good speed up, 5.1x, and it gets 100% recall because it answers all of the cast check queries. And finally, we come to QueryMax. So there are a variety of configurations for QueryMax, and we discussed one of them. So the purple cross, which is within this red circle, gets a speed up of 24x and a recall of 92%. So you see that this point is somewhere in between an application-only analysis and a demand-driven analysis. So it gets both good speed up as well as good recall. Now, let's look at the null point analysis, and I'm going to go over this faster because the results are pretty much similar to the cast check. So the whole program analysis gets no speed up and perfect recall. Then the application only analysis gets a very high speed up, but a low recall. And QueryMax gives a bunch of configurations which are in between these two extremes. So it gives a good speed up, but also a good recall. Now let's look at the related work. So there are three main directions. The first is a library summary based analysis. So the idea here is you construct a summary of the library, and then you use the library summary instead of the actual library code when doing the static analysis. And we already saw an example of this approach in Avros. The second direction is demand-driven analysis. So demand-driven analysis is the most efficient on a per query basis. This is well accepted. But when there are a large number of queries, like when we want to analyze all queries of one client in an application code, it may not be the fastest because it adds a little bit of overhead. And finally, the third direction is an analysis of program fragments. So this direction tries to analyze program fragments in isolation and then combine their results. So in conclusion, our motivation was that what we wanted to speed up an application-only analysis, but without losing any precision. And our approach was we select a partial library that is most likely relevant to the application, to the client analysis queries. And all the pointers, all the library pointers outside of our selected partial library are treated as a bottom element in the abstract domain. The result is that we get 10x speed up, 100% precision, and 87% recall on average. So in this case, we trade off a little bit of recall for speed up, as opposed to existing techniques which traded off precision for speed up. And so our results are more in line with what users expect from static analysis tools. And that'll be all for this presentation. Thank you all for listening.